and one lecture on probability. So we did linear algebra stuff, which included linear regression and PCA. We had a lecture on causal inference from our first industry speaker. Then we had a lecture on probability. Then one algorithm attached to it was this naive Bayesian classifier. And I would recommend play with it. It works usually much better than you would expect such a dumb algorithm to do. It does pretty good. Usually that's my feeling about naive Bayesian classifier. So I recommend you play with it too. And now we are going to our second lecture on probability. So to warm up, let's start with a simple example. First, I actually put some of it as an exercise already. So if you had time to look at exercises, you did some of it. Maybe the first one. So we got two random variables, x and y. They are both a uniform number between 0 and 1. Anything between 0 and 1 has equal chance. That's what a uniform number between 0 and 1 means, right? And now let's compute the density of x. So how did we define density? We first defined cumulative distribution function, CDF, right? Then we defined PDF, probability density function. So what was that CDF? Let me remind you that thing right here. CDF, usually we denote it with capital T or capital P, means probability of x being less than t. Okay, what would that be if your x is a uniform number between 0 and 1? Well, if t is less than 0, no way, right? It's always between 0 and 1. If somebody says, what's the probability of x being less than -5? No way, right? Okay. How about if t is like bigger than 1? If somebody asks you, what's the probability of this thing being less than 10? Well, you're going to say for sure. It's between 0 and 1. It's always less than 10, right? So what matters seems to be when this number is between 0 and 1, essentially. So I think it's going to come out like this, like if t is less than 0, no way. If t is bigger than 1, for sure. And if it is between 0 and 1, literally t, right? Why? Because let's say somebody asks you, what's the probability of this number x being less than half? Well, it's been between 0 and 1, less than half is literally half, right? So that's why I'm trying to think like probability of x being less than t for a number t between 0 and 1 is literally that number t, nothing else. Yeah. Yeah, yes. This is literally a continuous guy that is a uniform number between 0 and 1. You only know this thing is between 0 and 1, and that's it. Okay? Anything between 0 and 1 has the same chance for you. That's what it means. So let's think about it. What's the probability of a uniform number between 0 and 1 being less than or equal to half? Right? Half divided by 1, half. So how big is this part versus how big is the total thing? Since the total thing is 1, everything is very simple. Okay? You are getting there yet, okay? Okay? So far, so good? Yeah, okay. Now, when I know the probability cumulative distribution, to get the density, what did we do? Just take the derivatives, right? So the density of this guy, usually denoted with little p. Sometimes they will also put an x to remind you that this is the density of this x, is derivative of this guy, and derivative of t is nothing but 1. Okay? Now, if you like, you can connect this back to your integral interpretation. If you take integral of 1 from 0 to here, it will give you 1 times half. Okay? So I start from uniform because it's the most kind of simple thing you could do. So far, so good. Does it make sense to you guys? So we look at the cumulative distribution, then we took the derivative, then we got the density. Sometimes it also goes the other way around. Sometimes you know the density in your problem, then they ask you this, then you integrate. You only need to know the relationship between them. This is a cumulative guy. This is an instantaneous guy. So the picture representation of this, not for uniform, but in general, you will have a curve, and the curve will be the density. And then when they ask you the cumulative, you integrate until the point T. Because area under a curve is integration. The curve represents how much density, how much kind of weight that randomness is putting right there. For this particular uniform guy, it's pretty simple. Let me draw it. The picture will look like this. It's always between 0 and 1. And the density is always 1. When somebody gives you a T and asks you this cumulative, you literally look at the area under this. What's the area of this rectangle? 1 T, 1 times T, T. Okay, right? So the main point is density is some sort of instantaneous change. Cumulative is by name. It's a cumulative thing. Cumulative means integral. Density means derivative. So far, so good. Okay. And if usually, yeah. But sometimes one of them is given to you. That's why I was talking about the relationship. You start peeling from somewhere, right? Either from distribution or density, and sometimes it's given to you. You find the other one there. All right, pretty good. Now let's try to go for the second one. We had these two independent random variables. And someone tells you, I just did an experiment with the second one. It came out as half. What's the probability of first one being less than half, less than equal to? Well, then you would say they are independent. This information gives me nothing, okay? The second one being half tells me nothing about the first one, so you can just ignore. And what's the probability of being less than half? Less than t, so it is half. Okay. How about the third one? Now they tell you minimum of this 2 is 2 over 3. What is the probability of x being less than half? Zero. Yes, because if the minimum is 2/3, x can never be less than half, right? X can be at least 2/3. So pictorially, minimum 2/3 means when you draw them, they are known to be bigger than 2/3. They live here. Okay. If you find this type of question silly, there is a reason that when you understand the basics well, the rest kind of follows. Okay. So that's why I'm warming up from basics again. All right, now the last one. Now they tell you the maximum is 2/3. What's the probability of x being less than half? No. So maximum is 2/3 is given. Well, 2/3 is bigger than half. So there is a probability that x can be less than half now. I don't know. We have to think about this. Like, what if x is the maximum? Then I already know it's 2/3. But if x is not the maximum, then it has a chance, exactly as you said. So I'll give you a minute or two to think about this. Now it's the first time I'm asking you something non-trivial, okay, in this example. So far, I was giving you little toys to play. This is again a toy, of course, but yeah. Think about it a minute or two. And you don't have to figure it out right now, just like think about it. This will get you going, then we will go with the rest of our lecture. Yeah, maybe you can divide the entire thing into 2 pieces. Good idea. Divide your universe into 2 pieces. In one, x is max. Then you know it's 2/3. There's no chance it's going to be less than half. In the other one, y is max. Then you're going to know y is 2/3, but then it doesn't affect x at all. You know. So yeah, you're getting pretty close. Yeah. This basically now gives you information. Okay. So what was the definition of conditional probability? Let me just remind you that. So probability of A conditioned on B was probability of A intersection B divided by probability of B. So, you're going to start from the basics and build it up. I'll not do it now. I'll leave you as a fun brain teaser to deal with. Try not to work on this when I'm lecturing you. Okay, work on it after the lecture. But at the end, you need to think about it. But when you know something about the maximum, it's A information about your random variable X as well. Okay, now that we kind of warmed up, let's get going. So what did we do last time? We talked about conditional densities, right? Like if you have X and Y, X conditioned on Y was given like this, or Y conditioned on X was given like this. Or in other words, the joint of X and Y is the same thing as density of X times Y conditioned on X, or density of Y, X conditioned on Y. All right. Then we talked about conditional independence. If they look like the first one, they're already independent, sometimes written like they're orthogonal to each other. If they don't look like it, sometimes when you condition them on another random variable, they start looking independent. That's called conditional independence. And a pictorial way to think about it is this, like we had in this causal inference lecture. Kind of Z kind of explains X and Y. It's kind of the mindset here. Okay, that's something we talked about last time. Then we talked about bias rule or bias law. And I included a nice video about this on our canvas. If you want to have like a mental picture for bias law, I would recommend watch that video. It's very nice exposition, gives you a whole bunch of pictures to think about bias law. That's one of the most basic things in probability. I forgot too, there was a quotation. Bias law is to probability what is Pythagorean theorem to geometry, something like that. It's that basic. All right. And then, this bias law for events looks like this, and then discrete random variables looks like that, and then the same thing for density looks like that. This is all the same idea. This is discrete. This is continuous with density. It's all the same idea, right? And then we started working on this coins example. If you remember, there were like 3 coins, one of them biased. A priori, we don't know. They all look the same. Then we do an experiment. We get HHT. And we were computing what's the probability of first one being biased. Or let me remember the question. Yeah, but you can, of course, ask also what's the probability of third one being biased as well. We started this, and you are going to complete it in exercises. If you didn't, go back and do it when you get time. Okay, do it soon so that bias law kind of sticks to your head, right? Okay, very good. That was the bias stuff. So far, so good. And then we talked about this naive Bayesian classifier. I put a link on Canvas about this to an open source textbook. And their code looks pretty good, so that's why we did not bother to write another notebook. And they have code in JAX, TensorFlow, and PyTorch, whichever one you like, you can use. I don't know too much about JAX. Does anyone, do we have a JAX Pro? Anybody who has a lot of experience? It's kind of new, not so new. JAX, J-A-X. It's a differentiable programming library, essentially. It's supposed to be more functional than TensorFlow. It's developed by Google people now. It started a bit independent. Yeah, it's something like PyTorch and TensorFlow. Think about it that way. But I did not use it much, so I don't have personal experience. Okay. All right, let's get back. But it seems to be doing pretty good stuff. That's why I asked if there is any pro, maybe we can learn all together. All right. Anyway, so this was now. I did the recap of last lecture, and we are warmed up. Let's get going with some new information, new knowledge. So I'll give you some classic random variables that people use all the time. One classic is Bernoulli. Bernoulli is like a coin flip, but it may be biased, okay? So say 0, 1, heads or tails, but it doesn't have to be half-half. It could be P1 minus P. That's what Bernoulli is, okay? And another one called geometric random variable. This goes like this. You try until you succeed, whatever succeed means in your particular context, okay? Suppose I'm rolling a dice and I need a 6 to get out of the prison in Monopoly. So my success is to get a 6. What's the probability of getting a 6? 1 out of a 6, right? But maybe I don't get it in the first try. Then I try again. Then I try again. What's the probability of my success being in 8th trial or say 10th trial? Fail this many times, get successful at the end. So 5 out of a 6, say 9 times, 5 out of a 6, 5 out of a 6, 5 out of, you multiply them all. And in the 10th trial, let's say you got your 6 with this probability done. That's a geometric random variable. If you have this kind of situation, you would usually use geometric random variables for modeling. And this shows up in all kinds of places. The next one, called categorical random variable, abbreviated cutely as CAT, is a bit more general than Bernoulli, actually. It looks complicated, but not so complicated. Okay, let me explain it to you. Let me roll up a little bit. So what is CAT in this context? You got some options, 1, 2, 3, 4, n. Okay, the image you're seeing might be a cat, might be a dog, might be a dinosaur, whatever. Okay, so there's like n options. Okay, or a dice, for example, could be a categorical random variable. You have 6 options. Okay, it's something simple. Then every category will have a weight, C1, C2, C3, Cn, and they should sum up to 1. Then the probability of your random variable going into the ith category is Ci. That's what a categorical random variable is, right? For example, let's say you got 3 categories here, and then 1/3, 1/2, 1/6. This is your categorical random variable. Sometimes you would see the vector of this C1, C2, Cn, and they would just write cat of that vector. That means you are defining a random variable where the probability of that random variable landing in the first category is this, landing in the second category is that, etc. For example, for this random variable, first category is this probability, second is this, third is that. In short, they would just write it as cat of this vector. Categorical random variable of this vector. First category, this probability, second this, third that. Okay? Does it make sense so far? Yes, go on. I is usually a category. Like, usually this is coming from classification type stuff. Like let's say I see Adam, I have no idea who this dude is. I'm like, 2 categories, reasonable guy, crazy guy. Okay, say that's it. So, or like you see an image, 10 categories, say. So that's how you should think about it, like this thing landing in one of those categories. But you're right, you could think about it more abstractly as well. This is usually coming from this categorization type context. That's why they call it this way. Otherwise, it's just a simple random variable. Probability of random variable being the I, being 1, being 2, being 3. Say you can express a dice this way too, if you like. It being 1, 1 out of a 6, being 2, 1 out of a 6. Then for this language, dice would be cat, 1 out of a 6, 1 out of a 6, 1 out of blah, blah, blah. Okay, that's about it. So far, so good. This you would see all over the place, so it's good. You get used to it. You might also rebel and say, it's just making something simple complicated. If you say that, I hear you. That's what I thought too when I first saw this. But people use it all the time. Okay, you better get used to it and use it. Okay, now the next thing that you'll again keep seeing all the time is called soft max. So what does this mean? So one general idea that nowadays we seem to implement all the time, we would like the operations we put in our algorithms to be kind of differentiable, or at least something smooth, not like very discrete. We don't want it to jump from a value to another value all of a sudden. We want it to be a little more smooth, okay? But max operation is not so smooth. You take a whole bunch of numbers, take the max of it. As an operation, it's kind of very discrete. So this is your smooth approximation to max. That's how they come up with this wording. You have your vectors, collection of a whole bunch of numbers, right? And one of them is the biggest. You can call like max of this vector is the biggest one. That will be your max operation. Why do they call it softmax? Raise all these numbers on top of exponentiation and divide by the sum of all these exponentials. Now what happened is, since the sum of all coordinates is 1, you created a probability type situation. Moreover, suppose this guy was bigger than the rest for the sake of discussion. Say A1 was the biggest. When I raise it to the power of E, it's going to become much bigger. You know, how big it was will get amplified. Then this coordinate will look much bigger than the rest. So you will see who was the max. Okay. But that's why it's called softmax. So you're not pushing it to be max. But if you create, again, a categorical random variable where you use these probabilities, probability of your random guy going to the max category will be the biggest. So far, so good. That's a softmax operation. What it does, if you think about it in a modular way, it takes a vector, turns it into a probability distribution. Okay, that's what it does. So far, so good. You're still alive. Surprise. So everybody's still alive. Hope you're not on your Facebook in your laptop or something. All right. And, you know, this is like as if ith category is that probability. That's what I was talking about. So far, so good. With only these definitions, categorical, random variable, and softmax, we can build logistic regression right away, right now. But if you bear a couple of minutes, I'll tell you a few more random variables that you will keep seeing, then I can do logistic regression afterwards, okay? A few more minutes of patience. You guys okay? And if you do that few more minutes of patience, you will be apparently ahead of a lot of our graduates. So how do I know that? So one day, an executive from HEB calls the math department, and I'm very happy that I'm not the chair of math department because he had to answer that call. And the guy is totally furious. He says, you know, we hire your UTSA people. That's what we want to do. We are local HEB headquarters this year, right? And then we have like this 5 people who have undergraduate degree from CS, math, whatever, that kind of disciplines, that is working in our blah, blah modeling team. I forgot that detail. And these guys are trying to model discrete stuff with continuous random variables and continuous stuff with discrete random variables. So what the heck you're teaching to these kids? You know, so the guy is so furious, he decides to call up the math department and says, can you please teach these guys at least what's a discrete random variable and what's a continuous random variable before you ship them off to our place so that we can train the rest. And this was 3 years ago. I forgot the exact date. But of course, then the chair called a meeting with everybody who teaches probability. You know? Since I teach some probability courses, time to time I was in that meeting. And luckily that none of my students was that bad, turns out. It wasn't my fault. Anyway, so the point is, try to be aware of what kind of random variable has what kind of nature. So far, we are talking about discrete in the examples I gave you. But let's do some continuous. So this is our Gaussian, the normal random variable. The density of Gaussian will be given to you as follows. If it has mean, mu, and variance sigma squared, I did not define variance yet. It will be done hopefully today. You know, bear with me. So your Gaussian will always have 2 things attached to it. Mean means it's average, it's mu, and sigma squared, it's variance, okay? Let me at least draw you a picture. So a Gaussian with this density will be usually written like this, and it will look, the density when you plot it, will look like this. Around the mean, it has its peak. And how big is this? Like, it's going to look like a peak and then going down. Roughly speaking, how big is this? Directions will be as much as the standard deviation. Okay, variance is the square of standard deviation. That's intuitively what it means. We will get the precise definition later, right? This is your Gaussian. And the issue with Gaussian is it gets small very fast. Okay. So if I would be keeping to draw this thing, it's going to go small like very fast. We would call this light tails. So the tails here, they're pretty light. And sometimes this creates too much sensitivity. If you're trying to fit some Gaussian random variable to your data, and if you would have an outlier somewhere, suppose you had some data points, you're trying to fit this guy, and there's an outlier here, it will mean too much for your Gaussian. It's too sensitive. And because of that, this student T distribution was invented. The guy who invented it was working for a brewery in Dublin, Ireland, and he had very few samples from the beer, and he needs to fit some distribution. And the samples are screwing up the Gaussian, and I forgot his name, and everybody forget the name because he was called student in all the papers. The company did not allow him to write with his name so that they will lose their competitive advantage to other breweries in Ireland and whatnot. So he invented this distribution. It is kind of smooth distribution, but the tails are not this thin. It has a bit heavier tails. So when you have only few data points, like this person had, and when you're trying to fit it, an outlier doesn't kill entire enterprise. Okay. Yeah, go ahead. So light means it decays rather quickly. Heavy means if you plot the density, this will not be decaying so quickly. It's a little heavier. That's what it means. And I'll give you more pictures in a sec. Okay. All right. This is student T distribution. And I don't remember on top of my head the density. Okay. And you don't need to remember it as well. Just know that this thing exists. And it is a lot less sensitive than Gaussian to outlier data. Right. Very good. And another one called Laplace. So what's the difference between these three? Since this has e to the blah blah squared right there, if you put an x a little bigger, it gets squared and put on top of e. So it becomes a very small number. So Laplace does not have that square. It only has an absolute value. So this decays slower than Gaussian. And it is not as complicated as student T. Okay. Now let me show you some pictures of these standard random variables. Here are some pictures. Let's look at them together. Maybe I should zoom in. I did not like the resolution so much. Yeah, let me zoom into first picture, then we can zoom into the second one. Okay, so let's see what we are seeing here. So here, the Gaussian you're seeing is mean 0, standard deviation 1. Okay. And then you're seeing a Laplace and a student. Okay, it's all written there. So you can read for yourself. And see that Laplace has the biggest peak. And Gaussian has pretty quick decay compared to the student T. And that's kind of all you need to know for this moment, okay? And the other picture here. So in here, they're fitting a distribution to data. You have Laplace, student T, and Gaussian. And in the first data, there are no outliers. It's cleaned up. And in the second data, there are outliers. And you are seeing the effect of outliers to the fit. And when you look at it, you see the student T, the red one, did not change as much. Okay. But when you look at what happened to Gaussian, you see it was almost looking like the Laplace here. It's hard to see the difference. But here it is rather different. The peak got like pressed so much because it's trying to capture the outliers. Okay? Yeah, right. Yeah, that is true. It's higher. That I have to think to answer, yes. What you say sounds intuitive to me too. I have to think a little more to answer this. But here my main point was like this one. This versus what you're seeing here. Yeah. It's a good point. I'll have to think about it a little more. That's a very good question. So outliers are right here, as you see. Okay. Yeah, I don't want to give a hand wavy, potentially wrong answer. Let me think a little more and give you a good answer. Okay. All right. Okay. So these are your standard distributions that you would usually see all the time. So please, if you see something continuous, don't use the Bernoulli or some other discrete stuff. I don't want to get another call from HGV people, right? And if you see something discrete, try to be careful what random variable you're using. There is something called central limit theorem that we will see today or in the next lecture. That is about using Gaussians to approximate something very discrete. Okay. If your discrete has too many options, sometimes it's legitimate to use something continuous like a Gaussian, but you kind of need to know when you can do this. So we'll talk about it. If your discrete is just like a dice, you got 6 options, you don't use Gaussian, of course. But sometimes it's discrete, but too many options, like say 1,000,000 options. Maybe then it starts looking like continuous. Okay, that's the idea. Okay, now I can tell you what logistic regression is. But before I do so, let's kind of motivate or warm me up a little bit. Let's say these are 2 different classes of data, and you would like to split them up into 2 classes, okay? And let's say first try, I want to try something linear. I'm trying to draw a line between these 2 classes that will split them as good as possible, you know? If I draw a line right here, say like this, maybe, I don't know, then you'll probably need to put also some restrictions on the line. Otherwise, you might say, I'm just going to put it right here. I'll split them. Okay. I'm trying to illustrate the idea, so let's not do that kind of crazy stuff. So what I'm trying to tell you is this. If this is your line, one of those purple dots claim to be in the same class with this red dots. Moreover, this red dots here and purple dots here are also claimed to be in the same class now. Let's say above the line is one class, below the line is another class. So this is very bad for classification. Okay, let me play with this a little more. Like, I don't know, maybe something like that. Yeah, this is better, but still hard. So my point being, using a linear classifier, depending on the geometry of data, fails very quickly. Okay. So you would like to have your decision boundary a little more maybe curvy so that you can fit stuff easier. That's what logistic regression is going to do. The decision boundaries are going to start looking like this. Since it's curvy, it's pretty easy to split these 2 colors of data to 2 classes. If I would try to draw a linear decision boundary, it gets harder. So logistic regression is called a linear method. Even I wrote it here. In the books, you will see linear model for classification. So there are 2 lies in logistic regression. First, it's actually not a regression method. It's a classification method. Second, it's not really linear, but it's still called linear. So there are two lines to debunk about logistic regression. Regression is a very bad wording, actually. Regression means like you're kind of trying to fit some random variable against another. And it's not what this thing is doing. This is trying to classify data. Right? First lie. Second lie, it's not really linear, but kind of linear. And you'll see what I mean by that soon, okay? Okay. Now, how does logistic regression go? It goes like this. You got your data points, x1, x2, x capital N. And suppose they got D features. They're living in RD. And suppose this is your labeled data, and you know every single one of them, which class they belong to. Suppose there's n different classes, dogs, cats, I don't know, horses, kangaroos, whatever. These are your images, D features. This is your labeled data. They belong to different classes, and you would like to fit a supervised model to this data. Okay, and what's the model? The model is called linear because it goes like this. It takes your features of your vector, multiplies it with a matrix. It's like a linear thing right now. And then you're allowed to add some bias. You're allowed to push them in some direction also, it's okay. Then on top of this linear thing, you put your softmax. As soon as you put your softmax, I'll remind you once again what is the definition of this. It actually loses the linearity entirely because softmax is not linear at all. And after you put the softmax, now you got a vector here, right? What softmax does, it takes a vector given by this, turns it into another vector where it starts looking like a probability distribution. And you take that vector, you make it categorical distribution, that is your model. So let's try to unravel the definition by going back to what I told you a few minutes ago. I see people taking notes, let me wait. Okay. So let me remind you the definitions once again. Where is softmax? It is right here. Softmax was taking a vector. In logistic regression, this vector will be W times X plus P. Okay? That's why it's called linear. The way you create the vector you put inside softmax is a linear thing. Then after that, you put it inside softmax. Now it doesn't look linear at all. There's a whole bunch of exponentiation. And after you put it inside softmax, you put it inside categorical. So this becomes literally like your probability distribution being in the first category, this probability, second this, third this, etc. That's what the model is going to spit out. And let me get back. Of course, I'll show you some illustrations. So far, does it make sense to call this our model? Any questions so far? You take your vector of features, multiply it with your matrix W, add a bias term to it, and then put a softmax on top, then turn it into a probability distribution. And now what you're going to try to learn is the best matrix and the best bias so that the probability distribution we created gets pretty close to actual labels. Okay, that's what we want to do. So far, so good. Any questions? Now, of course, I just said it, like I want this probability distribution to be close to the actual label. What do I mean by that? So what do you mean a distribution close to another one? This is first we need to think about. Then we need to turn it into an objective function. Then optimize over all choices of W and B to make that objective function maximized. That's how it is going to go. Almost everything you do in machine learning and data science is secretly an optimization problem. Also, most of the statistics as well. So you'll have some objective, and you're trying to maximize or minimize. Okay, don't try to remember this because a lot of people forget it. I don't know why. Okay. Now, what would be an objective function? So let's see. I got my data. And suppose I do what I just said. And for every data point, it spits out a distribution now. It says first data point, gives me a vector with n coordinates. And that says being in the first category for this data point is this much probability, second this much probability, third this much probability. So for every single data point, your model spits out a probability vector, okay? Now, the truth, though, just looks like this. In the truth, I know the first data point is in the fourth category. So the true label is going to be 0001 here for sure, and there is no other probability at all, okay? So now I'm talking about making something like this close to something like that, okay? So how do I reason about this? So now the first thing you need to ask then, how do I reason about two probability stuff being close or far from each other? At the end, what I'm doing is like I'm attaching a probability to every data point, and the truth is also a probability, even though it's very funky, it just has 1 and the 0 for the rest, but where that 1 is changing for every single data. Okay. One way we measure distances between two distributions comes from something called information theory. But before I say anything, anyone heard of something called KL divergence? They would throw this buzzword. Anybody? No? You heard of it? So when did you hear it? Like in a bar or whatever? That was your pickup line? Okay. So when did you hear about KL divergence? I see. Exactly. So now that's going to happen to you again, looks like. So you're KL divergence, not today, but you'll hear that soon again in this course. Yeah, so the question is like, I got two distributions. How do I measure close or far from each other? Okay. So back in the day, okay, maybe not KL divergence, but I hope you heard of this guy called Shannon and his entropy notion. So Shannon's entropy notion is behind all these projectors and satellite communications and everything. And one thing he defined was called entropy. Let me define you entropy. In the case of a random variable with only two values to simplify the situation. Suppose this is your Bernoulli random variable. It takes 0 or 1. So I'm going to get back to this distance very soon. Okay, bear with me a minute or two. And then let's say it takes value 0 with probability p and value 1 with probability 1 minus p. It's like a bit, say, you know. And here's another one, not the same probability. And the entropy attached to this random variable is you take that probability and you multiply it with its logarithm. And you take this probability and you multiply it with its logarithm. And then to make things nice, you'll need to put a minus in front. That's called entropy of the random variable. What does this mean? Suppose, for example, the deterministic case, if this would be 1 and this would be 0, what would happen? Here you will get a 1, log 1 is 0, nothing from here. And then here you'll get a 0. 0 is going to get multiplied with another 0. So for convention, we say 0 log 0 is 0, even though it doesn't make too much sense. At the end, in the deterministic case, entropy will be 0. The intuition for that is entropy measures how random is your random variable. Okay. If it is deterministic, then there is no random. It's very predictable. And if it is like, say, a million choices, picking 2 of them with very high probability, the rest kind of ignoring, that's not really random. It's going to 2 options most of the time. But if it is going to all million choices uniformly, it's looking very random. The entropy should be high then. And actually, this is the highest entropy you could ever take. If it is a discrete random variable, and if it is treating all the options in equal ground, that's the highest entropy. You can prove this mathematically, okay? So that's what entropy is supposed to measure. How random is your random thing actually, okay? And for our deterministic, for example, you expect that entropy to be 0 because it's just deterministic. It's putting a 1 to correct label, 0 to rest. Very good. Now we are going to use this entropy to measure distance between two distributions. So this was my X distribution, this was my Y distribution, and this, you see the definition of entropy for them. And I did not tell you everything about the entropy. Even though if I would tell you everything about it, it will still remain kind of mysterious. So Shannon, when he defined this and used it to do a whole bunch of communication, he didn't have a word for it. He said, this is what I defined. He was talking to this famous guy called John von Neumann. He was behind this nuclear bomb and many other things, a famous mathematician. Also, CS people, you heard of von Neumann architecture? So the same guy does, I don't know how many things, okay? Same person, just one person. And then Shannon, when he defines this and finds it very useful, he doesn't know what to call it, goes to von Neumann and says, I defined this, it works. I have no idea what to call it. And he says, call it entropy. Since no one understands what entropy is, you will always win any argument. So you'll be fine. Okay, so this thing is always kind of mysterious. And now we use it to measure distance between two distributions. Here is the measure, cross entropy. Take the first probability from your first distribution. Don't multiply it with the log of itself. Multiply it with the log of the other guy. Take the second probability, multiply it with the log of the other guy. Are you able to follow the difference between entropy and cross entropy? Cross entropy is supposed to measure how similar are these two distributions to each other. And if you just Google cross entropy loss, you will see it popping up all over the place wherever there is machine learning and data science. Okay, this is a very common thing to use. It's not the best thing to do, but it's at least a decent thing to do. Yes, correct. We are trying to, we'll get there very soon. Now, this was for distributions with only two values, 0 and 1. But for many values, it's going to be almost the same expression. Okay, so let me show you the many values version. Yeah. Yes, uniform would be the highest, deterministic will be the smallest. For discrete, uniform will be the biggest, and it will be log n if you have n choices. For continuous, Gaussian usually comes up as the biggest entropy. Somehow in the continuous world, Gaussian is the most symmetric, kind of treating everything in equal ground guy. In the discrete world, every choice is the same, like a dice is the most fair one, turns out. Okay. You can actually connect entropy to fairness questions as well. We will not get into that. But this is a very important topic as well. Since now we are deploying these data-driven models all over the place, there are rumors even Department of Justice is deploying, but it's not, as far as I know, publicly documented. At the end, you're deploying a machine model on a human decision. You need to be very careful about fairness. You know, of course, you're aware it's deployed on, say, giving somebody a loan or not. That's a very human decision too. If a person can get a car or not. It's being deployed on scheduling interviews for job applications, etc. So fairness is a terribly important question, just out of topic for this class. Now, our objective function is going to come out from this cross entropy. Now I have n options. Take the first probability, multiply it with the log of the other. Sum up, this is your cross entropy loss, okay? And I'll put a notebook about using this for some training today. And now my objective function now is going to be minimizing the cross entropy so that the distribution that your logistic regression is creating is as similar as possible to the actual labels. If cross entropy is high, these two distributions are very different. That's how you should think about it. The small means they are closer to each other. That's like a distance notion, okay? So you put the true label as a distribution, the stuff logistic regression is creating as another distribution, and you measure cross entropy for every single data point. Because remember, for every single data, logistic regression gives you a probability estimate, and there's also true label. So you can measure distance between these two distributions for every single data point. Then you sum it up through all your data points, take the average, that's your objective, okay? You wanna minimize this, and you will say then my logistic regression is producing something that is close to actual label, right? When you train it on some data, the good point is, of course, you can use it later on some different data. Logistic regression is not like something like PCA. You only use it on the data it's seen. You can train it on some data and use it on some different data. Okay, very good. This is how it goes. You minimize this cross entropy, and that's it. Okay. And you'll have a notebook about logistic regression on Canvas when this lecture goes on Canvas. People also use some different vocabulary to talk about quality of the model you produce. Let's say you're trying to use logistic regression, God forbid, for cancer recognition. Okay, don't do this, but let's say you did it. Okay, it's get some image data in. It's going to spit out either malignant or benign, 2 options. Okay, then you check it against the label given by doctors. You might have false positives or false negatives. Then how are you going to reason about this? There are some specific words people use. Some of it will be in your notebook today. And we will get into more details, I think 2-3 lectures from now. This goes under the name decision theory. I'll tell you all that words in detail in that lecture, okay? How do you think about like false negative, false positive? How do you think about accuracy of your model? And then maybe again, maybe you heard this in a bar again, something called ROC curve. Have you heard of this? Yeah, same machine learning bar. There is also this notion of ROC curve, whatnot. This we will talk about 2-3 lectures from now in a more comprehensive and detailed way. Today in the notebook, you will see some of those words being used. Okay, pretty good. So far, everything is based on linear plus softmax plus categorical. That's how logistic regression works. Now you can do a dirty trick and make it much stronger. Okay, so what is that dirty trick? It is called polynomial feature extension, or called lifting trick. What is it? You take your data, it's got D features to it, right? And you start combining the features with each other. I'm writing here the dirty trick for degree 2, which means take 2 of them, multiply, and think about all such multiplications you could do. I take the first feature with itself, Z1 squared. I take the second feature with itself, Z2 squared. Do all that. And then like take Z1 with Z2, Z1 with Z3. You know, think about all that stuff. Now, what did you do? Now your data had D features. Now, after you did this dirty trick, it's looking like it's got D squared features. Now, why would you ever do this? Well, features are usually not independent from each other. So this is supposed to capture, hopefully, after you train your model, relationships between the features. So what do? You do logistic regression on here with D squared features, not with D features. Everything else will remain the same. Whatever I told you, it's going to be right here. That's why I called it a dirty trick. You don't change anything in your algorithm. You're just adding one more press step to your algorithm, which is taking your D features, expanding out many features, okay? And this is degree 2 version. You could do degree 3, degree 4, up to your liking. Okay? That's called polynomial feature expansion in a lot of libraries. They do this automatically. You don't have to worry about it. And now let me show you pictures on how does this look like. Yeah, you do your logistic regression after the lifting. And the first picture, let me zoom in. This is something I think is a decent illustration. So suppose this was your correct decision boundary, like a circle, okay? It's going to be hard for you to capture this right up with the logistic regression. But you know the equation of a circle is like a degree 2 thing. X1 squared plus x2 squared equals blah. If you lift it up to degree 2, your model can capture this pretty easily. Because after lifting up, it starts looking like linear. You kill that degree 2 thing, okay? That's kind of the intuition behind this. Your decision boundaries maybe has to be pretty complicated. But when you lift your data up with many more features, they might be captured by a linear thing. because linear on top of a degree 2 lifting is actually quadratic. And this decision boundary is quadratic. Okay, that's the dirty trick. The more lifting you add, the stronger your model gets. Of course, there will be a point of diminishing returns, but also probably your memory can start dying if you don't have a nice GPU, but that's basically the idea. Let me show you some pictures done with this dirty trick. This is pictures from your textbook. And the good thing about the book is it has the code available for every figure right there. So if you want to see the source code, you just go to your PDF and click. It's on GitHub. Decently written code. I was amazed how this guy had the time to do this, and I realized he works for Google. He makes the interns do all this code. So you would see different names attached to the code. All right. Exactly. So in the left, this is the original situation. You are trying to put the logistic regression on it. And in the right, you just do quadratic, which means degree 2. And immediately you see it's able to capture a lot more complicated boundaries for classification. Okay. And it's the same algorithm. You just lift it up. Syntax-wise, there's only one more layer, basically. Lift it up first, then do the logistic regression. Okay. Okay, here's another one. This is the usual one. B looks degree 2 lifting. This guy looks degree 4 lifting. You see, it's already doing pretty complicated stuff. And then there is like train and test errors. They train it on some data and they test it on the rest of the data. And there is, as usual, there is a point of sweet spot. If you increase the degree so much, you see after some point their error gets increasing. Like degree 4, degree 2. Well, why do you think this is happening? Okay, go ahead. Exactly. So the model is overfitting. So when you increase the power of the model, it's fitting to training data so well. Anything else you give to it, it starts failing miserably. Okay. It actually does its job perfectly. It fits to your data, but you don't want to use it on your data. You want to use it on some data that you have not seen yet. That's going to be always a running theme throughout the course. Okay, that's logistic regression. Now, any questions? I have about 15 minutes or so. I'll do some more probability, but before that, let me pause and check if there are any questions. Yeah, vectors, this is easy to do. Images, if you turn them into vectors, you can do this again. Yeah. Yes. Images looks like, for the moment, convolutional nets, and there's more fancy versions like transformers are the current winners. We'll get to that soon. Whatever that convolution means and why would you make it used for images, we'll get that. All right. So far, so good. Looks like everybody's okay. Yeah. Yeah. Very good question. You can do the same for linear regression as well. Do the lifting, then do your linear regression. Then they would usually call it polynomial regression. Since linear on top of lifting looks like a polynomial now. You are talking about, let's say, 3x plus 5y. Now you're talking about 3 times x times y plus 5 times y squared. Now the thing you create looks like a polynomial. Lifting trick plus linear, you might sometimes see it called polynomial regression. But that fancy word is exactly what you said. There's nothing so much fancy about it. Yeah. Very good. Now let's do some more probability. So punchline for me is linear logistic regression is literally softmax on top categorical distribution. That's your model. And you're trying to find the best matrices and the bias to do that. So this is your logistic regression. In a lot of resources, logistic regression is presented as if it is something too complicated. What I'm trying to say is it's not too complicated, okay? Linear, softmax, cat, that's it. And if you want to be more fancy, instead of before linear, make this lifted so you have a whole bunch of features. That's about it. Okay, let's go back to probability. Okay, so a little bit up or down. Okay, so good. Okay, we are done with now logistic regression. 15 minutes more of probability. We got our random variable, and it's got a density. Suppose it's a continuous thing. How do you compute its average, also called mean? Put your values there, multiply them with the density, integrate over. Okay. Integral, you could always think about it as some sort of cumulative operation. Okay. So you say my random variable taking value 100 comes with the density at that 100 point, you multiply them, you average over. So if your random variable would be discrete, let me write it, maybe then it's easier to see in discrete world. So this is continuous. Let me just here do a digression. Suppose you got a discrete random variable, it's taking values 1, 2, 3, n. Then the expectation would be go through all the values and attach them with the probability of this discrete guy being that value. So you see it looks pretty analogous. Instead of sum, you get an integral. Instead of probability of being that, you get density of being that. Okay? All right, that's average. Well, you don't have to take integral of just the value itself. You can put it to some power. You can take average of t squared, which would mean expectation x squared here. You can do third, it will be expectation of x cubed. They will be all given by this formula. So you might ask, why would you do that? Expectation of a random variable does not tell you too much about it. It's just the statistics you collect about it. Okay? If you base your decision off of just expectation, very likely things will go wrong. The more moments you know about it, squared, third, fourth, the better you can understand how that random variable behaves. These are all called summary statistics about your random variable. You'd usually see mean, this thing I just told you, and standard deviation, which I will define in a sec. But that's not the end of the story. You could collect as more moments as you like. For example, one of the earliest instances of this that I know existed is Carl Pearson, sometimes called father of statistics. So he was collecting data about crabs in South Italy. Okay. And then he's expecting like a Gaussian distribution from the length. He says it's got to be like a normal curve. And then no, turns out it's not a normal curve. Then he's trying to fit the actual distribution. He literally computes the moments up to, I think, 6th moment by hand, and then solves the best fit of a mixture of Gaussians by hand. And then that's how he figures it out. That's the earliest I know, maybe more than 100 years ago. These moments appearing in scientific literature, but this is a general idea. So let me define you the stuff you have seen before in this language. Variance or standard deviation are related only for the case k equals 2. K equals 1, expectation. 2 is related to variance and standard deviation. How do you compute your variance? You take expectation of x squared. Then you take your mean, you square it, you subtract. You're kind of trying to center. That's your variance. And variance means how much your data is going away from its expectation. For example, variance 0 would mean your randomness, there is no randomness, right? It's always sitting on the expectation. That's what would it mean. Big variance means it's going on and off a lot. There's a lot of jiggling, okay? This expression, sometimes you would see this for variance. It's equivalent to that. This is small algebra. Maybe I can give it as an exercise to you guys today. It's nice to work it out once. And standard deviation is square root of variance. Okay. Somehow we decided to go by square root instead of the thing itself. That's called sigma, usually standard deviation. Sigma squared is your variance. All right. So now let me show you a picture before I tell you more. So far, so good. Expectation, kth moment for any k. And the second moment gives you, second time the first moment gives you the variance and standard deviation. Okay. Let me show you a picture. I'll get back to what I was going to say here later. Here is something called data source. Okay. This is a whole bunch of data. It is 2D data. I'm going to tell you how to think about average and variance and whatnot when you have 2 dimensions. But intuitively, it shouldn't be so hard to follow. All these data sets, they have the first expectation the same, and also the second moment the same. Okay, whatever standard deviation means for a 2D data set, it's the same for them. Their average is also the same. Okay. So of course, this is constructed for this purpose. It's not real data. But the point is, the summary statistics doesn't tell you too much about your data. So you'll see people throwing this words all the time, expectation this, standard deviation this, then we know everything about it. No, that's not the case. Okay? And this is a nice picture to keep in your mind. It's from your textbook. There's also source code and whatnot right here. They all have summary statistics the same. Okay. Now you might ask, do they not tell us anything at all? No, they do tell us some stuff, and we will get there soon. Either this lecture or next lecture, I'll tell you what you can extract from expectation and standard deviation. Now, let me get back to what I was just doing. Sorry for my voice trying to escape from me today. Okay, good. Now we talked about expectation, which is average. We talked about kth moment, and the second moment gives you the variance and standard deviation. And I showed you a picture called data source, which gives you a whole bunch of different data sets, which has the same expectation and same variance. Okay. The next thing you would do about this kind of stuff is conditional expectation. What does that mean? If you have some information, your computation of the mean value will change. That's what it means. Let's say I'm talking about average temperature in San Antonio. That's my expectation. And if I know the month is August, then compute the average temperature, you will give me a different expectation. Right? So that's what conditional expectation is. More precisely, if you know a random variable y is taking value b, and if you're asking what's your expectation for x conditioned on this, take all the values x can take your conditional density, fix your y on b, because this is what's given to you, run your x on all values t, take the integral. This is conditional expectation when the value of the second random variable is fixed. Okay? So far, so good. Sometimes you might want to do something a little more abstract, which is, well, what if I don't fix the second random variable's value? I just say, what is your expectation on x conditioned on y? What would that even mean? Okay, so I told you what it means when you know what is the value of the second random variable and you're basing your estimate on x on top of it. What would this mean is like, this is one level of abstraction. This means whenever your second random variable takes value 5, this thing will take expectation of x conditioned on y equals 5. Whenever it takes value 10, it will take conditional expectation of x based on y equals 10. So this is going to be a general expression on all possibilities that can happen with your second random variables. Okay, so this is something random itself. And this is after this, probably I'll stop. This is a good point to stop to confuse you, then let you go. Right. So this conditional expectation confuses a lot of people when you first see it. It's going to be looking like this. Suppose this is my universe. And my random variable y can take values 1, 2, 3, 4, 5. The conditional expectation of x conditioned on y, this thing, is going to be another random variable. And the values it takes is, when you ask the value here, it's going to take this number. When you ask the value here, it's going to take this number, etc., etc. Okay. So conditional expectation written this way is a random variable itself. And this is extremely useful, turns out, even though it looks kind of funky idea. This is behind a whole bunch of stuff. Okay. All right, and let's see. Apparently, I still have a minute or two. Very good. And this is recorded. This was how you defined conditional of expectation of x conditioned on y. And why? How would you use it? One of the most common uses of this is this fact. Let's say you're trying to compute the expectation of a random variable. It turns out to be a hard thing to do. You cook up another random variable y, like an auxiliary one to help you. And in that cooking, you should make sure this part is easy to compute. Then your expectation becomes like a two-layer thing. Expectation over y inside conditional expectation. And we will probably start back from here, and we will apply it to compute the expectation of a geometric random variable. Yes, John, do you have a question? Very good question. Then y wouldn't help you at all, because x conditioned on y will be still x. Usually you cook up something that is dependent on your x, but kind of unravels its behavior. For example, for geometric, I want to understand what is the expected number of steps I take until I see my 6. Okay. That seems like, I don't know, is it 100, 200, 1, 5? Kind of complicated. So we are going to cook up a random variable which will unravel, which will make it easier to understand. You usually cook up something dependent, which kind of allows you to see what's going on. So very good question. Thank you. That's it for today. And if you got confused with this conditional expectation, you're not alone. Happens to everyone. We will recap and move on from there.